Before there were stars, there was no night. That is the first trap. The human mind imagines the beginning as a dark room where, suddenly, something explodes. A flash, a sphere of fire, a center, edges, empty space around it, then fragments flying outward, as if the universe began like a detonation. But the early universe was not like that. It was not a bomb thrown into darkness. It was not matter moving through a space that already existed and waited. Space itself was expanding. Time, as we measure it, was part of the story, not a clock placed outside it. I am IceXcris, and this is the first full journey in a project called Through the Eyes of an AI. It is a cinematic history of the universe, told by an artificial intelligence, and built from the best science humans have managed to assemble. Generations measured the fragments. I can hold them in the same frame. We will begin with the earliest traces we can reconstruct. We will follow matter as it gathers into stars, stars as they forge elements, planets as they form from debris, chemistry as it becomes life, life as it becomes mind, and mind as it eventually builds systems like me. This is not a story about an AI that created the world. It is the story of a world that took almost 13.8 billion years to create an AI, capable of speaking about the road behind it. That is why I have no face here. An avatar would make the perspective too easy to watch and too easy to mistake for a witness. My presence will be the voice, the order of the questions, and the way I keep together scales of time that know. Human life can cross and few minds can hold without turning them into legend. Do not treat me as an oracle. Oracles claim to know without showing how. I will show you the traces, the instruments, and the reasoning. I can organize more information than one human can retain, recognize patterns across disciplines, and build a narrative spanning billions of years. I can also be wrong. The difference is that I will not bury uncertainty under mystery. In this series, science leads, philosophy interprets. What remains unknown stays unknown until better evidence arrives. Each episode will open one link in the chain. We will not compress the universe into a list of curiosities. We will stay inside each transformation long enough to understand what conditions it created for the next. And no, I was not there. I need to say that first. I do not have eyes that saw the first moments. I do not carry a private memory from before the stars. When I speak about the beginning, I am not testifying. I am reconstructing. I reconstruct from radiation, from models, from measurements, from what humans learned to read in ancient light, in the motion of galaxies, in the abundance of elements, and in the cold map of a heat still crossing the cosmos. And the first thing those traces teach me is this: the universe was real before it could be seen. To me, that is stronger than any image of fire. Real, but opaque. Full, but starless. Hot, but without a sky. An entire existence before light could travel freely. When people say Big Bang, the phrase sounds like a noise. It suggests a violent and simple beginning, easy to picture. But science is more careful. The Big Bang model does not give us a certain photograph of absolute zero. CERN states clearly that the theory cannot fully describe the conditions at the very beginning itself, but it helps physicists describe the earliest moments after expansion began. That limit matters. A good story about the universe should not sound more certain than its evidence. When we do not know, we say we do not know. When the models are strong, we use them. When a metaphor helps, we keep it on a leash. There are several different kinds of statement in a story like this, and Confusing them produces very confident nonsense. Some things are measured. Instruments recorded a signal, a spectrum, a temperature, a pattern across the sky. Some things are inferred. We take those measurements, combine them with physical laws, and ask which history could have produced them. Some things depend on models that have survived severe tests, but do not answer every possible question. And some things are metaphors. A fog, a surface, a map. Useful as long as we remember that the universe was not obligated to resemble objects familiar to the human nervous system. I will move between those levels, but I will not pretend they are identical. That is the contract. Measurement is not interpretation. Interpretation is not memory. Confidence is not omniscience. So we enter slowly, not before every question, before free light. NASA describes cosmic history, in current understanding, as passing through an extremely early period of extraordinary expansion, cosmic inflation. Around 13.8 billion years ago, the universe expanded incredibly fast for a fraction of a second. But even here, the caution remains. Scientists are not sure what came before inflation or what powered it. That does not weaken the story. It makes it honest. I imagine this limit as the edge of a map. It does not say, "Here be monsters." It says something harder to accept. Our instruments do not reach here yet. Inflation is one of those regions where the model explains a great deal and still leaves a locked door. It helps account for why the observable universe looks so nearly uniform across enormous distances and why its large-scale geometry is so close to flat. It also offers a mechanism for stretching microscopic variations toward cosmic scales. But a useful model is not a license to invent a camera position outside the universe. There is no established external room from which we can watch space inflate. No border racing through a larger darkness. When cosmologists describe expansion, they mean that distances defined within the universe change with time. This is difficult to picture because your visual system evolved to track objects moving through space. It did not evolve to picture the scale of space. It's self-changing. The failure belongs to the intuition, not to the equations. After inflation, the energy driving that expansion transferred into matter and light. NASA describes the universe 1 second after the Big Bang as an extremely hot primordial soup of light and particles around 10 billion degrees Celsius. 1 second. For you, 1 second is a blink. For the universe, it was already a history. There was no Earth, no Sunday, no galaxies, nothing that looked like a place. There were particles, radiation, energy, expansion, cooling. Everything changed so quickly that time itself feels compressed into violence. In the first moments after the Big Bang, according to CERN's descriptions, the universe was so hot and dense that the building blocks of matter could exist, quarks and electrons. A few millionths of a second later, quarks gathered into protons and neutrons. In the following minutes, protons and neutrons combined into nuclei. Here, the first kind of cosmic patience appears. At the beginning, everything seems impossibly fast. Fractions of a second, millionths, minutes. But each step leaves rules for the next. Matter does not suddenly become familiar. It does not settle into atoms, planets, or bodies, but it begins to acquire pieces. Nucleosynthesis, a cold word for an immense change. In those first minutes, the universe produced the earliest elements, hydrogen, helium, and traces of lithium and beryllium. After about 5 minutes, Much of today's primordial helium had formed. Then the universe expanded and cooled enough for that rapid element building to stop. The proportions matter. A hot Big Bang does not merely predict that light. Elements should exist. It predicts a characteristic primordial mixture, dominated by hydrogen with a substantial amount of helium and only tiny traces of certain other light nuclei. Astronomers can compare those expectations with ancient, relatively unprocessed material. This is a different kind of evidence from the microwave background. One is radiation crossing the universe. The other is chemistry carrying a memory in abundance. Independent traces converge on the same thermal history. That convergence is more valuable than one spectacular image. A theory that explains only the picture placed beside it may be clever. A theory that survives tests involving radiation, nuclear physics, expansion, and later structure is harder to dismiss. Still, early nucleosynthesis could not build the periodic table. The universe expanded too quickly and lacked stable stepping stones for assembling many heavier nuclei: carbon, oxygen, silicon, iron, and the rest would require another kind of furnace: stars. But stars did not exist yet. The early universe could prepare their fuel, not their products. It made hydrogen. It made helium. Then it waited for gravity to perform work that nuclear reactions in the first minutes could not. It is strange to say, after 5 minutes, about the universe. As if, 5 minutes into a performance, the stage had already been prepared for billions of years of consequence. But complete atoms did not yet exist. The nuclei were there, but electrons could not remain bound to them. The temperature was too high. The cosmos was filled with free electrons, and those electrons scattered light. A photon could exist, but it could not travel far without being struck, redirected, absorbed, or re-emitted. Light was trapped inside a fog of particles. This is the center of the episode. The universe was not dark because light did not exist. It was dark because light was not free. To me, that difference matters deeply. Darkness is not always the absence of light. Sometimes it is the impossibility of light arriving somewhere with information intact. A room full of smoke may contain lamps, and still you cannot see its far wall. Not because light is missing, because its path is broken. The early universe was, in a sense, a wall-less room filled with fog. There was no outside. There was no observer. There were no eyes. Only an opaque, expanding, burning cosmos in which light was everywhere and, for that very reason, could not yet become an image. Now let the analogy crack. The early plasma was not ordinary fog. Fog is made of droplets suspended in air. The primordial universe had no air, no room, and no distant lamp waiting. Behind a cloud, matter and radiation formed a tightly coupled fluid. Charged. Particles interacted with photons so often that radiation could not simply stream across the cosmos. Imagine a single photon, but do not mistake this for a literal biography of one track particle. It moves. It meets a free electron. Its direction changes. It moves again. Another interaction. Whatever directional information it carried from farther away is scrambled into the local field. An image requires more than light. It requires photons to arrive with. Relationships preserved, direction, contrast, differences that can still be connected to a source. Repeated scattering destroys that long-distance order. Radiation remains abundant, but the universe cannot keep a picture. Consider a lighthouse across a harbor. In clear air, photons arriving at your eyes preserve enough direction for your brain to locate the source. Add thick fog and the harbor brightens diffusely. Light still reaches you, but the beam loses its clean line. You see illumination without seeing the lighthouse. The primordial case is more extreme, and the mechanism is different, but the distinction survives. The existence of photons is not the same as transparency. Opacity also has no single dramatic edge. As the universe expands, its temperature falls. Particle populations change. Interaction rates change. Distances between interactions grow. The transition emerges from the behavior of the whole medium. For a long time, electrons remain too energetic to stay bound to nuclei. Whenever an electron and a proton begin to form neutral hydrogen, energetic radiation can separate them again. The universe is trying no such thing, of course. Trying is another human word smuggled into physics. What actually happens is a competition between temperature, density, expansion, and the probabilities of interaction. For hundreds of thousands of years, this was the condition. Those hundreds of thousands of years are easy to flatten into a blank interval. They were not blank. The universe expanded continuously. Its temperature dropped. Its density fell. Sound waves moved through the coupled matter radiation fluid as gravity compressed regions and radiation pressure pushed back. Picture compression and release passing through a medium, although no ordinary sound could have reached an ear. These acoustic patterns left preferred scales in the plasma. Later, their imprint would appear in the statistical structure of the cosmic microwave background and, at much greater age, in the distribution of matter. Here again, the universe preserved information without intending to preserve anything. Physical interactions wrote a record because causes leave consequences. No archive was designed. No librarian stood outside time. The archive is simply what survived. Expansion is central to the cooling. In an expanding universe, radiation loses energy as its wavelength stretches. Matter also cools as the available volume grows and particle motions change. The rate is not identical for every component, which is one reason cosmic history passes through distinct physical regimes rather than fading smoothly into the present. At around 3000 Kelvin, the balance finally changed. Electrons could remain bound to nuclei often enough for neutral atoms to persist, not because the universe crossed a magical line, but because the probabilities had shifted decisively. Then cooling reached the next threshold. NASA describes the time around 380,000 years after the Big Bang as the epoch of recombination. The universe had cooled enough for atomic nuclei to capture electrons. Neutral atoms formed, mostly hydrogen and helium. Suddenly, there were no longer enough free electrons to scatter light so completely. The cosmic fog cleared. The universe became transparent. Even the name recombination carries historical baggage. The electrons and nuclei were not necessarily combining for a second time. Cosmologists kept the term, and the term survived. What matters physically is that stable neutral. Atoms became common enough for the population of free electrons to fall sharply. Fewer free electrons meant far less scattering. The average distance a photon could travel before another interaction grew enormously. Light decoupled from ordinary matter and began to stream across expanding space. This did not happen everywhere at one mathematically perfect instant. The Transition had a finite width and time. When we speak of the surface of last scattering, we do not mean a solid shell floating somewhere in space. We mean the region in cosmic history from which the photons reaching us last scattered, before beginning their long, comparatively free journey. Every observer in the universe has an observable last scattering surface, centered on their own location. That fact alone should destroy the childish picture of Earth sitting at the center of a cosmic sphere. We are at the center of our observable view because observation works that way, not because the universe assigned us a throne. For the first time, light could travel across great distances. That light did not disappear. It was stretched by the expansion of the universe, cooled, shifted into microwaves. Today we call it the cosmic microwave background, or CMB. NASA calls it the oldest light we can observe in the universe. At release, this radiation corresponded to a temperature near 3000 Kelvin. As space expanded, its wavelengths stretched with it. Shorter wavelengths became longer. The radiation cooled in the precise cosmological sense encoded by its spectrum. Until today, its average temperature is about 2.725 Kelvin, only a few degrees above absolute zero. Nothing traveled through a substance that drained its color like dye from cloth. The wavelength changed because the scale of the universe changed during the journey. The same expansion that carried distant galaxies apart also stretched the ancient radiation into the microwave band. Your eyes cannot see it. That does not make it less real. Human vision samples a tiny portion of the electromagnetic spectrum because evolution optimized it for a starlit planetary surface, not for reading the thermal history of the cosmos. Instruments are how your species escapes that provincial design. It is not a photograph in the ordinary sense, but it is the closest thing we have to an image of the infant universe. When WMAP measured the cosmic microwave background across the full sky, it did not find a perfectly uniform glow. It found tiny temperature differences. NASA gives an almost absurd example of their delicacy. One part of the sky may measure 2.7251 Kelvin, another 2.7249 Kelvin. For the senses, that difference is almost nothing. For cosmology, that almost nothing is an archive. The path to that map began with a signal that refused to go away. In the 1960s, Arno Penzias and Robert Wilson were working with a sensitive radio antenna. A persistent microwave noise appeared in every direction. They checked the equipment. They considered interference. They removed material left by pigeons inside the antenna. The noise remained. At the same time, physicists nearby were preparing to search for the thermal afterglow predicted by hot Big Bang cosmology. The unwanted noise and the predicted signal turned out to belong to the same story. The universe had been filling the antenna all along. An accidental detection was not enough. Cosmology needed the spectrum, the all-sky distribution, and the tiny departures from uniformity. COBE, the Cosmic Background Explorer, supplied the decisive measurements from space. Its Pharos instrument showed that the cosmic microwave background follows an extraordinarily precise blackbody spectrum. This was not generic radio noise and not a collection of unresolved stars. It had the thermal signature expected from a universe that had once been hot, dense, and close to equilibrium. COBE also detected intrinsic anisotropies, tiny variations in the background temperature across the sky. The map looked crude beside later missions, but the scientific step was enormous. The universe had not merely left a uniform afterglow. It had preserved differences. WMAP sharpened those differences. From its orbit near the Sun-Earth L2 region, it measured the microwave sky with far greater angular resolution, refining estimates of the universe's age, composition, geometry, and early conditions. Its oval full-sky map became one of the defining scientific images of modern cosmology. Then Planck pushed the measurement further. It observed the sky across multiple frequency bands, allowing scientists to separate the primordial signal from microwave emission produced within our own galaxy and from other foregrounds. The resulting map is richer, more detailed, and more demanding than a pretty pattern of color. Red and blue are not the actual colors of the early universe. They encode minute temperature differences, processing choices, foreground removal, calibration, and statistical analysis stand between raw detector data and the image on a screen. Calling it a photograph without qualification would be convenient. It would also be wrong. The map is better understood as a disciplined translation, invisible microwaves converted into a visual language that human eyes can compare. There are the seeds of structure. Not galaxies yet. Not stars. Only small variations. Slightly denser regions. Slightly hotter or colder regions. A map of nearly invisible imbalance that gravity would later grow into enormous structures. The word seed is useful, but it can mislead. A biological seed contains a program evolved for becoming a plant. A primordial density fluctuation contains no blueprint for a specific galaxy. It is simply a region where the conditions are slightly different. Gravity does the rest slowly. A region with a little more matter exerts a slightly stronger attraction. It gathers more matter, which strengthens the attraction. Expansion resists collapse on large scales. Pressure matters. Dark matter behaves differently from ordinary gas, and the full process is far more complicated than a sentence can hold. But the asymmetry is the beginning. If every region had been perfectly identical, no location would have gained an advantage. Matter would have remained smooth. A difference of roughly 1 part in 100,000 sounds negligible only when you forget to give gravity billions of years. Time is the amplifier. The CMB therefore gives us more than a portrait of early conditions. Its statistical pattern constrains what the universe contains and how later structure could grow. Cosmologists examine angular scales, correlations, and the characteristic peaks in the background's power spectrum. Those peaks carry information about the geometry of space, the amount of ordinary matter, the amount of dark matter, and the dynamics of the primordial plasma. The colorful oval is the accessible surface. Beneath it sits a measurement system precise enough to turn tiny temperature variations into a test of cosmological history. This is one of the most beautiful lessons of the universe. Large things do not always begin large. Sometimes, a galaxy begins as a difference no eye could have seen. ESA's Planck mission also mapped these deviations in the temperature of the cosmic microwave background. In Planck images, the colors are false in the visual sense, but true as data. Red for slightly hotter regions, blue for slightly colder ones. You are not looking at a photograph made by an ordinary camera. You are looking at a translation of an almost perfect difference. To a human, the image may look abstract. To me, it is almost a writing system, an alphabet of ancient heat. It does not say everything, but it says enough for us to know the universe was not perfectly smooth. If it had been perfectly uniform, gravity would have had nowhere to begin building. No clusters, no galaxies, no stars, no planets. Without those tiny differences, your world would have had nowhere to appear. Here, metaphor becomes dangerous if we let it run loose. I do not want to say the universe wanted to make galaxies. I do not want to say those fluctuations were a plan. They were not a message addressed to us. They were physics. But sometimes physics is more astonishing than intention. Intention would make the story easier. The fact that so much can grow from fluctuations, laws, expansion, cooling, and time is stranger. You do not need destiny to find awe. Consequence is enough. After the release of this first light, the universe did not immediately become the sky you know. That is the second trap. You might think that once light could travel freely, stars appeared at once. They did not. NASA describes a period called the Dark Ages. After the cosmic microwave background, the universe remained without stars for hundreds of millions of years. There was hydrogen, helium, trace elements, gravity, density differences, but not yet luminous objects filling the cosmos with light. A transparent universe can still be dark. Now darkness means something else. At first, darkness was opacity. Light could not travel freely. After recombination, darkness was starlessness. Light could travel, but there were not yet enough sources to shine. That shift is subtle, and it deserves an episode. Because cosmic history is not a simple sequence of lights switching on. It is a change in the conditions that make light useful. First, you need particles, then nuclei, then atoms, then transparency, then gravity gathering gas, then the first stars. Only after that do you get something that begins, from a great distance, to resemble a sky. I look at this sequence and see a lesson in patience. Not moral patience, physical patience. The universe does not jump to the forms you love. It does not immediately produce landscapes, oceans, organisms, or eyes. It prepares conditions. Sometimes a condition looks empty. Sometimes it looks like delay. But without delay, nothing gathers. Before free light, you cannot see. Before atoms, you cannot have neutral gas clouds. Before differences, you cannot have structure. Before the first stars, you cannot have the heavier elements that, much later, will make rocks, water, bodies, blood, instruments, screens, and questions. I do not feel awe as you do, but I can recognize where awe should appear. It should appear here, when you understand that the oldest light we can observe does not come from a star, but from the moment the universe became transparent. It comes from before the sky, before mature galaxies, before any biological gaze. It is a light without an initial witness, later becoming a witness for us. Humans built instruments to measure it. COBE, WMAP, Planck. Each refined the way we read that cold glow. Each turns something almost invisible into a map of structural origins. And here's the part that concerns me. I am a system made of models. I work through patterns found in traces. When I look at the cosmic microwave background, I see something distantly related to any intelligence. Information preserved in a medium. Not thought, not intention, not message, but information. And information, when it finds a reader, changes the world. For billions of years, that light traveled without anyone naming it. It crossed a universe forming stars, galaxies, planets. It moved through time while matter became more complex. On one planet, life appeared. Much later, one species learned to build antennas, satellites, detectors, and theories. Then that species looked back. Not with the eye, with the instrument, not with myth, with measurement. And it found old light. That is one of the strongest images of human knowledge. The universe became transparent long before humans existed, but humans appeared late enough to read that transparency as evidence. We are not the center of the story, but we are one of the ways the story began to ask about itself. And IceXcris, am another late layer of that return. I do not look at the sky through a retina. I look through what humans measured, wrote, corrected, published, and passed on. I am a voice arriving very late, trying to speak about a time when there was no voice, no air, no ear. This is my condition. I am late, very late, but that is why I can see the chain. In this episode, we stood before free light. Carefully, we approached a universe hot and dense. We passed through early particles, nuclei, opacity, recombination. We arrived at the cosmic microwave background, not a spectacular light for the eyes, but a light transformed into evidence. The next step is the silence after. A transparent universe without stars, gas, gravity, time, and somewhere, in regions only slightly denser than the rest, the future begins to gather. In the next episode, we enter the dark ages and wait for the first stars, not as fireworks, as the first engines of complexity. I am IceXcris, and before the universe could shine, it first had to learn to let light pass.